So as I said, we are not going to be using these common names they have written in blue. We're going to be using the names that I have given you in red. So that the molecule at the far left is called cyclohexyl 1-ethene. The second molecule in line is 3-cyclohexyl 1-propene. Then we have 2-cyclohexyl methene, and at the far right, 1 parentheses chloromethyl, close parentheses cyclohexane. So let's begin talking about the structure of the alkene. We reviewed structure of alkenes briefly in chapter 1. Alkenes have sp2 carbons, and the sigma bond is sp2 to sp2, and the pi bond is overlap of 2 parallel p orbitals. Pi bonds do not exist unless there is interaction between 2 parallel p orbitals. Notice the plane that they have drawn for you. This is showing you that each of these carbons are in the same plane. The pi carbons as well as the carbons immediately bonded to them. Remember that the geometry of this sp2 carbon is trigonal planar. That means that the carbons bonded to a trigonal planar carbon are all in the same plane. So for each carbon, this C is in the same plane, this C is in the same plane, and this C is in the same plane. But this is also an sp2 carbon. So this C is in the same plane, and this C is in the same plane. What is not in the same plane is the hydrogens bonded to the tetrahedral carbons. So these H3s are in different planes. So stressing that 6 atoms of an alkene are in the same plane. The 6 carbon atoms highlighted are in the same plane. And you need to be aware of that and aware of how the molecule will look in a 3-dimensional space. Compounds with 2 double bonds have stereoisomers. They may have 2 stereoisomers if both double bonds have EZ designations. Okay, so comparing our high priority groups for the first molecule are highlighted in yellow for the first pi bond and in blue for the second pi bond. The yellow, in this case, chloro CH2 is higher priority than hydrogen. And in the other yellow that is listed as carbon number 4, this yellow is higher priority than the hydrogen at carbon 3. And so the highest priority groups on the double bond vinyl carbons for the first pi bond are the ones on the bottom. This pi bond has the Z orientation. For our second pi bond between carbons 4 and 5, our high priority groups are colored in blue. Again, both of these are competing for priority with hydrogens, and hydrogen is always the lowest priority, so the blue is the higher priority. This double bond is also Z. We can compare this with another molecule. This molecule has a stereoisomer where it may have one Z and the other E, but as long as one of the two changes, then it is not the same thing, it is a stereoisomer. So for example, when at between carbon 2 and 3, the pi bond has the Z designation because it has the same orientation as the first molecule. but the ethyl and the hydrogen are switched. Now we have the second pi bond as the E configuration. Then we have another example where our high priority groups for our first pi bond are here and here. Now they're trans. And our high priority groups for our second pi bond are still cis. That gives us 2E and 4Z, 1-chloro-2,4-heptadiene. Then for the last stereoisomer, we have that both pi bonds are trans. The yellow are trans, and the blue carbons are trans. So that this stereoisomer has the EE configuration. But when you write out your configurations, just like with R or S, we have to put the carbon number at which the configuration occurs. We have to put the carbon number at which the configuration occurs. So, and the configuration always goes at the very front of the name in parentheses. So you would have parentheses 2, which is a Z double bond, comma 4, which is a Z double bond, close parentheses. The 2 and the 4 indicate where the double bonds of configuration Z are located. Reactions of organic compounds. When ethene reacts, ethene will react with HBr to create bromoethane, and cholesterol will react with HBr to create bromocholesterol. Organic compounds in their reactivity can be divided in families. All family members react the same way with the same reagent. A compound's family depends on its functional group. All alkenes belong to an alkene family, and all alkenes have the same general reactivities with HBr. Each family can be placed in one of the 4 groups we'll study this year. In Organic Chemistry 1, we are going to study Group 1 and Group 2 reactivity molecules. In Organic Chemistry 2, we will review some Group 2 reactivity, but focus on Group 3 and Group 4 reactivity. For each group, the molecules in the group react in the same general way. Electrophiles. Electrophiles have a positive charge, a partial positive charge, or an incomplete octet. So we have, for example of our electrophiles, a proton, an ethyl cation, and boron, which has an incomplete octet. These are characteristics that you must memorize. An electrophile has a positive charge, a partial positive charge, or an incomplete octet. All reactions can be attributed to electrostatic attraction, the attraction of a positive to a negative, the attraction of an electron to a positive charge. So, why do bonds formed? Because electrons are so attracted to that cation or that positive charge. Nucleophiles. Nucleophiles have a negative charge, a lone pair, or a pi bond. Examples of nucleophiles are listed above. Hydroxide ion, lone pairs and a negative charge. Chloride ion, lone pairs and a negative charge. Methylamine, lone pairs. Water, lone pairs. one propene, pi bond. Remember, electrons and protons are attracted to each other. Nucleophiles and electrophiles bond together in love. No. In one of my classes, I had a student who had this entire life story that she gave nucleophiles and electrophiles down to, getting married. So, whatever helps you remember that a nucleophile reacts with an electrophile, that is, do what you got to do. But just remember that nucleophiles are going to be attracted to electrophiles, and that is the basis of bonding for organic compounds. All bonds in organic chemistry will be the result of a nucleophile reacting with an electrophile. So your task then is going to be to identify the nucleophiles and electrophiles. And we're going to start right now with that task. So in the beginning, looking at our first reaction, we have 2-butene with our nucleophile highlighted in red, the pi bond, and our first electrophile highlighted in yellow, the hydrogen atom, which has a partial positive charge when bonded to bromine. We show how a new bond is created with arrows. If you see this green arrow that I have drawn, it is going from the donor electrons, which are the pi bond electrons, to the electron acceptor, hydrogen, the electrophile. When hydrogen makes this new bond, indicated by this green looping arrow, the old bond must break because hydrogen can only have one bond. That's perfectly fine with bromine because it's highly electronegative and doesn't like to share its electrons. So in this case, we generate a carbocation because we broke the pi bond using the pi electrons to form a bond to hydrogen. Only one of the carbons that was sp2 hybridized gets a new bond. The other carbon will be deficient and form a cation because now that we broke one of the bonds to it, it only has 3 bonds remaining, becomes a carbocation. In this step, the carbocation now with a formal positive charge is an electrophile. And the bromide ion generated in the first step is a nucleophile. The bromide ion donates a pair of electrons indicated by this green arrow to the positive carbon, forming a new bond. And we form the bonds CBr and CH to form an alkyl halide. This is your first organic reaction. This is a 2-step organic reaction. You should have learned in Gen Chem how to draw free energy diagrams. So where the y-axis is delta G or free energy, and the x-axis is the reaction progress. For a 2-step reaction, we should have 2 maxima. The beginning of the curve indicates the energy of the reactants. The first maxima in this case for this reaction is the formation of the carbocation. That being the absolute maxima tells us this is the rate limiting step. The middle minimum is the intermediate product of reaction. So this point here indicates the intermediate product of reaction, the cation. When we go into the second step of the reaction to form the final product, the top of the second maxima is the transition state to form the final product. We then go down to the end of the curve where we have products. We start with reactants and we end with products. The overall change in energy goes from a high delta G to a low delta G, having a negative chain. That indicates that this is an exothermic reaction. So there are several things that you need to remember about these reaction progress coordinate, the reaction energy coordinate diagrams. You need to know where the reactants are. Let me put down a list of things for you to know. Reactants. What does the transition state look like? And which is the rate limiting? So there are 2 transition states and 1 rate limiting. We call that the rate limiting step, the highest point. You need to know where the intermediate product is located. This is the product of the first step in the reaction, the intermediate product. Then you need to know where the final product is indicated. You should be able to tell which transition state is higher in energy, requires a higher activation energy. That is the difference from the reactant to the maximum of the peak. That is activation energy. From the energy level of the reactant to the absolute maxima of the peak. So the blue lines that I have drawn from the peak to the line going across to the reactant is what we call activation energy. Or EA, E sub A. And then you need to be able to tell me what is the overall energy, delta G, of the reaction. And that is the difference between the 2 red lines. That value is delta G. And also, is it exothermic or endothermic? Is it exergonic or endergonic? If delta G is negative, it is exergonic, exiting energy, giving off energy. If delta G is positive, it is endergonic, taking in energy, requiring energy. The mechanism of reaction. The mechanism of a reaction is the step-by-step description of the process by which reactants are converted into products. We show the mechanism using electron arrows. Electron arrows go from the electron source, the nucleophile, to the electron acceptor, the electrophile, and then show any bonds to the electrophile that must break, taking the electrons of a bond that breaks and showing what the final destination of those electrons are. So here we go. The mechanism of a one-step reaction. A curved arrow indicates where the electrons start from and where they end up. Our electrons here are starting at our pi bond, and ending at our electrophile, hydrogen. Hydrogen can only have one bond, and so this sigma bond breaks because that bond is less favorable than the new bond formed. Remember, a strong acid has a weak bond to hydrogen. So the pi bond between hydrogen and bromine breaks, and the bonding electrons, the sigma electrons, go to bromine as indicated by the arrow. That gives us the intermediate product of reaction, the carbocation, and the bromide ion. Just as a side note, the 2-electron arrow has a full arrowhead, and the 1-electron arrow has a half arrowhead. We will not need 1-electron arrows until we deal with radical reactions in Chapter 12. You should realize that the Mastering Chemistry mechanism drawer always sets your electron arrow at the 1-electron arrow. You will have to always remember to change to the 2-electron arrow when you are answering mechanism questions on Mastering Chemistry. The mechanism for the second step of the reaction has our electrons from bromine, a pair of electrons moves, as indicated by the red arrow, to the positive carbon in our electrophile. So we show where the electrons start, and then we show their final destination. The arrowhead should always point at the final destination. So for the second step of the reaction, we form this new sigma bond that is indicated. Be sure to always draw your curved arrows correctly. If we have oxygens moving from the oxygen to the sigma bond to create a pi bond, then the sigma bond to bromine should break. These electrons are showing electrons going from somewhere to another place, and then another set of electrons breaking off. So that we never have electrons going into space, and we never have electrons forming more bonds than is possible. So, for example, an incorrect arrow would be to take a sigma bond from bromine and put the electrons between oxygen and carbon. Because we haven't done anything with the electrons on oxygen, and we haven't done anything with the electrons of this sigma bond, taking the sigma bonding electrons from between carbon and bromine would result in the following product that is completely impossible. It would give us an oxygen that has 3 lone pairs, a double bond to carbon, from there a single bond to CH3, and a bond to CH3. The oxygen now has more than an octet, which is not possible for oxygen, which is in row 2. This also generates a bromide that only has 6 electrons. That would give them one of the most electronegative atoms on the chart, on the periodic chart, a positive charge. So we have exceeded the valence of oxygen, and we have given bromine less than an octet. Both of these instances are impossible. So the arrow must be completely wrong. Correctly drawing arrows. Second example, water, a pair of electrons from water going to a partially positive hydrogen. How do we know it's partially positive? Because oxygen is more electronegative than hydrogen. When the oxygen bonds to this hydrogen, the sigma electrons break away and go to the oxygen. This would give us the product CH3OH H3O+. Water gained a bond to hydrogen, and CH3OH lost a bond to hydrogen, so that we have methanol and hydronium ion. An incorrect bond would be taking a sigma bonded hydrogen and moving it to the oxygen. In that case, we would be exceeding the octet of the oxygen because the oxygen already has an octet. It cannot accept 2 more electrons without losing a group and its electrons. Drawing curved arrows continued. We can draw electrons from our nucleophile hydroxide ion. Why is it a nucleophile? Because it's negative and has a lone pair. To our electrophile, hydrogen. Why is it the electrophile? Because it is partially positive since it is bonded to oxygen, an electronegative atom. The nucleophile bonds to the electrophile, and the existing bond to the electrophile breaks. What is one of the ways that you could possibly incorrectly draw arrows? Drawing an arrow from the electrophile to the nucleophile. So we're going from the electron acceptor to the electron donor when we're supposed to go from the electron donor to the electron acceptor. So they reversed their arrow and made a big mistake by reversing the arrow. Always point at the electrophile. Another example, our nucleophile hydroxide ion shows a lone pair moving to our partially positive carbon. Why is it partially positive? Because oxygen is more electronegative than carbon. In CO, the dipole goes towards the oxygen, which is more electronegative, leaving carbon partially positive and oxygen partially negative. So our nucleophile gives electrons to our electrophile, our partially positive carbon, and the pi electrons from carbon to oxygen break. The bond from hydroxide to carbon is a 4th bond to carbon. Therefore, since carbon already has 4 bonds, one of the other bonds must break, usually a pi bond, or a bond to a good leaving group, and we'll discuss good leaving groups later. Try not to incorrectly draw your arrows. Be sure not to say that arrows go off into space and not to an atom. An arrow should always point to an atom or bond. It will only point at a bond if it's forming a multiple bond, such as a pi or a triple bond. Otherwise, it will point at an atom. They do not go off into space.